For 30 years, cosmology had a golden rule, a simple formula we believed could find the birth of the universe. The redder an object, the farther away it is. But we were wrong, completely wrong. The James Webb Telescope found two red dots, whose light seemed to come from just 100 million years after the Big Bang. According to the laws of physics, this was impossible. But the real shock wasn't their age, it was their motion. A single measurement, made 1 year later, proved it. They weren't at the edge of time, they were right in our own galactic backyard. If you think you know the universe, forget everything. Subscribe, because what we found is closer than you could ever imagine. Let's begin. For years, we had a perfect way to find the most distant corners of the universe. It was a method based on a simple, yet profound truth. A method that had worked thousands of times for 30 years. It was the bedrock upon which our understanding of the early cosmos was built. But then the James Webb Telescope looked there, and with a single observation, that 30-year certainty was not just questioned, it was completely shattered. Because, we now understand, the universe speaks to us in a language where the same word can have two completely different meanings. At the heart of this decades-long belief lay a technique astronomers call the dropout, or the Lyman-break technique. What does that mean exactly? Imagine the universe as a vast, invisible fog. This fog is made almost entirely of neutral hydrogen. The light from an extremely distant galaxy has to travel through this hydrogen fog for billions of years to reach us. And this hydrogen acts like a cosmic filter. It is a thief of light. It ruthlessly absorbs every single particle of light with a wavelength shorter than 912 Ångströms. Everything below is swallowed. Everything above can pass. This is why in the light spectrum of every distant galaxy, a kind of cliff appears, a sharp drop-off. Below this 912 Ångström limit, there is no light. It's gone. Above it, the galaxy's light is visible. For 3 decades, astronomers used this exact cliff to hunt for the most distant galaxies. They equipped their telescopes with different color filters that acted like a sieve. When they found an object that was completely invisible in blue filters, but suddenly shone brightly in red filters, it was clear. Bingo. They had found a candidate from the edge of the universe. This was an undeniable truth. But the real problem, it turned out, was not the method itself. The method worked. The problem was in how we understood what we were seeing, because this technique is inextricably linked to one of the most powerful concepts in cosmology, redshift. Redshift is not just a simple color change, it's a master key that unlocks two of the universe's greatest secrets: distance and time. Our universe is expanding, and the farther away an object is from us, the longer its light has traveled through this expanding space. This journey stretches the light waves, just like stretching a rubber band. The wavelength gets longer, the light shifts toward the red end of the spectrum. That's why a high redshift value, a Z value, means an incredible distance and a look far back in time. For example, the current record-holding galaxy, Jade's GS-Z140, has a spectroscopically confirmed Z value of 14.32. That number isn't just a number, it's a time machine. It tells us we are seeing this galaxy as it was, just 290 million years after the Big Bang. This in itself was a mind-blowing discovery. But the two red dots Webb found were playing in a completely different league. Their photometric redshift values were around a Z of 20 and a Z of 30. Let's think about that for a moment. A Z of 20 means a time when the universe was only 180 million years old. A Z of 30 means just 100 million years after the Big Bang. This was an era when, to our knowledge, even the very first stars had not fully formed, let alone an entire galaxy. There was simply no known physical mechanism that could assemble that much matter and ignite that many stars in such a short time. It was impossible. But even this impossibility was not the deepest reason for the science team's silence, because this perfect dropout technique had an Achilles heel, a blind spot that almost no one expected to be so extreme. This is where the secret and unexpected hero, or villain, of the story comes on stage, the brown dwarf. What is a brown dwarf? In its simplest definition, it is a failed star, a celestial body that failed to gather enough mass to ignite hydrogen fusion in its core. It's not a star, but it's much more massive than a planet like Jupiter. Since it has no nuclear fire of its own, it slowly cools over billions of years, and during this cooling, something very strange happens in its atmosphere. Especially in the coldest types, the Y-class dwarfs, temperatures are only between 300 and 400 Kelvin. That's not much hotter than a cup of tea you left on the table. These cool atmospheres are filled with molecules like methane and water vapor, and these very molecules do something crucial for our story. Just like the hydrogen fog in the early universe, they absorb light at specific wavelengths. And by a cosmic coincidence, this absorption creates a sharp drop in brightness, a spectral cliff, at almost the exact same wavelength as the Lyman-break of a galaxy, at a redshift of z equals 20, or z equals 30. So the universe was presenting us with two completely different suspects that left the same fingerprint, one at the absolute limit of observable time, the other in our own galactic backyard. One a flare from the dawn of the cosmos, the other the faint glow of a failed star. And the real problem was this. Just by looking at the pictures, just based on the colours, there was no way to tell which was which. We had a method, considered flawless for 30 years, for finding the most distant objects. We had a measurement that pointed to a physical impossibility according to this method, and we had an alternative suspect that could perfectly disguise itself as this impossibility. So, astronomers were faced with a fundamental question. Had they completely overturned modern cosmology, or had they fallen into the universe's most ingenious trap? This is why the team decided to do something that is almost a heresy in modern astronomy. They waited. They waited for 1 full year. Because there was one, and only one, absolute way to know if these two red dots were record-breaking galaxies or imposter brown dwarfs. They had to see if they moved. A galaxy at the edge of the universe does not move from our perspective. Its lateral motion over a human lifetime is 0. But a failed star in our own galactic backyard at the temperature of a cup of tea would definitely move. SO. The team had to wait an entire year to detect a tiny shift, smaller than the width of a human hair held at arm's length. It was a year filled with patience, doubt, and the anticipation of a single measurement that could change everything. But the place where these two dots were found was not a random patch of sky. On the contrary, it was perhaps the most famous and most intensely studied piece of sky in all of modern cosmology. Astronomers call it the bullet cluster. And that name represents an event that proved perhaps the biggest and strangest truth about our universe. The bullet cluster is the result of a collision between two massive galaxy clusters, a cosmic traffic accident of unimaginable scale. In 2006, a team led by Douglas Clow noticed something absolutely astonishing while studying this collision. The hot gas in the clusters, visible in X-rays, was gathered in one place, but the vast majority of the mass detected through the effect of gravitational lensing was in a completely different place. The mass was here, the gas was there. This separation could mean only one thing. A huge part of the universe is made of something we cannot see, something that does not interact with normal matter like gas, and reveals its existence only through its gravity, dark matter. The bullet cluster is the single photograph you show someone when they ask for proof of dark matter's existence. To this day, no serious counter-evidence has been presented. But the bullet cluster had another secret, a lesser-known but absolutely crucial one for our story. It is one of the most powerful natural telescopes in the sky. We call this effect gravitational lensing. What does that mean? The enormous mass of the bullet cluster warps the space-time around it, like a heavy ball bending a trampoline. The light from any object located behind it is bent and magnified as it passes through this warped space. It's as if the universe itself is holding a giant magnifying glass in front of the most distant objects. Galaxies that would normally be too faint and too far away to see become brighter and visible thanks to this cosmic magnifier. This is why, when astronomers want to look at the earliest eras of the universe, the first few 100 million years after the Big Bang, the bullet cluster is a natural target. It does part of the work for them for free. So, It was no coincidence that they looked right here. The combination of the Webb telescope's power and the bullet cluster's natural magnification was the most promising method for pushing the boundaries of the observable. So, on the night of January 20th, 2023, a mission called JWST, General Observer Program 4598, began. The principal investigators were Marusha Bradach, Alexei V, Filipenko, and Martin S. Sachs. Their goal was simple: to combine Webb's incredible power with the bullet cluster's natural magnifier and peer deeper into the universe's secrets than ever before. The telescope took images in 8 separate filters, from short wavelength 0.9 micron filters to long wavelength 4.44 micron filters. The exposure time for each filter was about 2 hours. At the end of that night, the deepest infrared image humanity had ever taken of this region was waiting to be sent to Earth. And in this image, a surprise that no one expected was hidden. Dozens of background galaxies, foreground stars from our Milky Way, technical artifacts. But then, in a corner of the field, just 12 arcseconds apart, were these 2 small, faint red points of light, and they looked different from everything else. They were perfect dropout candidates. They had the flawless signature everyone was looking for. But we know now what seems most distant may in fact be on our doorstep. So we understood the method, we understood the place, and we understood the 2 opposing possibilities. But what did these 2 red dots really mean now? What were the data whispering before the decisive measurement was made? And right then, as the scientists examined these first images, the quiet hope in the team gave way to something else entirely. A kind of awe, perhaps a little fear, because the data in their hands wasn't just saying they had found a new galaxy. The data was whispering that our fundamental understanding of the history of the universe might not be as solid as we thought. And now comes the real shock. Let's start with the most normal, yet still astonishing case. Jade's GS 14-0. This is the most distant, spectroscopically confirmed record holder galaxy, whose identity we are 100% sure of. It's not something that shouldn't exist, but it's something no one expected in this form. This galaxy's redshift is exactly 14.32. This number means the light reaching us from it has been on its way for more than 13.5 billion years. We see it in a state just 290 million years after the Big Bang. This is only 2% of the universe's current age. Previously, very few models predicted the existence of such a bright and distinct galaxy at such an early stage. And Jade's GSZ 14-0 was not alone. There were other candidates like it, found by different teams. The Webb telescope, even in its first years of operation, showed that the dawn of the universe was much more crowded and much brighter than expected. This situation led to headlines like JWST broke cosmology, because our standard model, the lambda CDM model, struggled to explain such efficient star formation at such an early time. The models were stretched, the limits were pushed, but nothing was broken yet. But this was only the beginning. The 2 dots in the bullet cluster were about to shatter these strained limits, and now we enter the first act of impossibility. Bullet BD2. This was the brighter of the 2 faint red dots in the images. This object started to become visible at a wavelength of about 2.77 microns in the F277WA filter. According to the dropout technique, this meant only one thing. The redshift of this object was approximately z equals 20. Let's digest that number for a moment. A z-value of 14.32 had taken us to 290 million years after the Big Bang. A z-value of 20 was catapulting us to 180 million years. There is a huge difference of 110 million years in between. This is a period of time just after the darkest ages of the universe. A time when, theoretically, the very first stars, called Population 3 stars, were just beginning to form. In this era, there should not have been a bright galaxy composed of billions of stars. This was physically impossible, because we do not know of a mechanism that could assemble so much matter and ignite so many stars in such a short time. No existing galaxy formation model could comfortably explain this data. Even the most audacious theories did not allow for such an early structure. This was not just a challenge for the standard model, it was a serious questioning. The team was holding an object from the earliest time of the universe that should not exist, and the worst was yet to come. Now we come to the point that pushes the limits of reason. Bullet BD1. The other, fainter, more mysterious second dot. This object wasn't even there in the F277W filter. It only appeared in the F356W filter at a wavelength of 3.56 microns, and it shone sharply in the 444W filter. This was the most extreme application of the dropout technique, and the result was breathtaking. The estimated redshift of this object was 30. Z equals 30. This number shouldn't even be uttered for a galaxy, because Z equals 30 corresponds to a time when the universe was only 100 million years old. This is an era when even the first stars were presumed to exist only sporadically and scattered, not to mention a galaxy. The existence of a bright object with a few thousand solar masses would have been a big deal. But what Webb saw was bright enough to be detected even with the huge magnification of the bullet cluster. This meant tearing up the entire existing cosmological timeline. If bullet BD1 were a real galaxy, then everything we knew about the early universe was wrong. Galaxy formation must have started hundreds of millions of years earlier than we thought. Or there had to be entirely new physics, an entirely new mechanism at work in the lambda CDM model that we didn't know about. This wasn't just breaking a record, this was a paradigm shift. All these discoveries, unexpectedly bright galaxies, the impossible galaxy at Z equals 20, and the mind-boggling possibility at Z equals 30, created a picture that no longer fit with our old understanding. The data was screaming that the early universe was faster, more efficient, and far more productive than our best theories allowed. But how could the scientists be sure they weren't falling for an illusion? How could they rule out the possibility that all these impossible objects were part of a cosmic trap the universe had set for them? This is why Bradach and her team did not share these results with anyone for a full year. Because if what they had was real, it would be the greatest discovery in modern cosmology. But what if it wasn't? They were stuck between these two extreme scenarios. On one hand, the greatest discovery in history. On the other, an inexplicable anomaly. Because sometimes the greatest discoveries are hidden not in the most distant places, but in the most unexpected ones. And this story had a precedent, a ghost, a case that had already sent the scientific community into a great excitement. Its name was Sears 93316. But astronomers gave it a more memorable nickname, Capitaro, and Capitaro was the living proof of why the bullet cluster team was being so incredibly careful. Capitaro was discovered in another deep JWST program called the Cosmic Evolution Early Release Science Survey, or SEERS for short, by Marco Castellano, Adriano Fontana, and their colleagues. This object, just like bullet BD1, had an incredibly sharp dropout signature. Its brightness increased by more than 15 times between the F356W filter and the 444W filter. This was the sharpest jump ever observed in an object. If this were a galaxy, its photometric redshift would be around 32, Z equals 32. That means a moment when the universe was only 90 million years old. Even more extreme than bullet BD1. Even more impossible. That's why the Discovery team avoided making a big claim in their paper published in February 2025. The very title of the paper reflected this deep uncertainty. They presented three completely different possibilities. Either this was a record-breaking, high redshift galaxy, or a much closer galaxy, shrouded in extremely dense dust, or an ultra-cool brown dwarf hiding in the disk of our own Milky Way. They were facing the exact same dilemma as the bullet cluster team, but unlike them, they didn't have the time to wait a year for a second observation to solve this mystery. Their story was left hanging in suspense, filled with doubt. And this doubt had enveloped the entire field. Because this problem of imposters was not limited to a single object. As Webb looked deeper and deeper, the number of such contaminants began to grow. In 2024 and 2025, teams led by researchers like Kevin Hainline published papers revealing a series of brown dwarfs masquerading as high-Z galaxy candidates in deep fields, like Jades and Sears. Lamia, Mauler, and York found 3 brown dwarfs mistaken for active galactic nuclei in 2023. Adam Bergesser and his team announced 7 more cold and distant brown dwarfs. This contamination was now a known, serious problem. No one just knew exactly how serious it was. Did the most extreme high-Z candidates found belong to this catalogue of dirty mimics, or were they real? It was a million-dollar question, and the Bullet Cluster team was in exactly this situation. They had 2 perfect dropout candidates in their hands. They were flawless, according to the standard method, and they were found in the field of the most famous dark matter picture in the sky, the most powerful natural lens. They could have published the paper. They could have claimed to have found galaxies at z equals 20 and z equals 30, and left the rest of the community to do the verification work. But they didn't. They chose another way. Instead, they did 2 things. First, they applied for spectroscopy time. They wanted to use JWST's near-infrared spectrograph, NIRCam, to break down the light of these 2 dots into its components and see what it really looked like. This was like a more detailed examination of the fingerprint. The spectrum of a galaxy and a brown dwarf should show distinct differences upon closer inspection. But, and this is more important, they did something much rarer in fast-paced modern astronomy. They applied for a second imaging epoch, and then they waited for 1 full year, because what they wanted to test with the second observation was a feature that a galaxy at the edge of the universe should absolutely not show: lateral motion. They would be looking for what astronomers call proper motion. If they found this motion, the entire interpretation of these 2 faint red dots would change with a single measurement. They would go from being the most distant galaxies in the universe to objects slowly drifting across the disk of the Milky Way in our own galactic neighborhood, pretending to be something else entirely. All the theory, all the possibilities, all the doubts were concentrated in this one test. But to truly understand why this test was so important, we need to dive deeper into the physics behind this cosmic deception. How is it possible that 2 so fundamentally different objects could send an almost identical signal to our best instruments? So, what's behind this? How can a galaxy at the farthest corner of the universe and a failed star in our own galaxy send almost the same signal to our telescopes? To understand this, we now have to dive a little deeper into the technique and grasp the physics behind this cosmic illusion. Because this story is the story of 2 completely independent physical processes that, by a strange coincidence, lead to the exact same result. It's time to enter the engine room of cosmology. It all starts with that method that has been the backbone of distant galaxy hunting for 30 years, the Lyman-break technique. To understand how it works, we have to imagine the universe as a giant hydrogen filter. This idea, proposed by Charles Steidel and his colleagues in 1996, was actually surprisingly simple. The early universe was made almost entirely of hydrogen and helium, and even today, 13.8 billion years later, the overwhelming majority of normal matter in the universe is still hydrogen. These countless hydrogen atoms, scattered between us and every distant galaxy, do something very specific to the light passing through them. They absorb any photon whose energy is high enough to strip a hydrogen atom of its single electron and ionize it. This energy threshold corresponds to a wavelength of exactly 912 Ångströms. Any particle of light with a shorter wavelength below this limit, the Lyman limit, that is, every ultraviolet photon, is swallowed by the intergalactic hydrogen it encounters during its journey of billions of years. Photons above this threshold, with longer wavelengths, continue on their way largely unhindered. Therefore, a sharp cliff forms in the spectrum of every distant galaxy. Above the Lyman limit, we see the galaxy's light. Below the limit, the light has almost completely disappeared. The reason this technique is so powerful is that the universe is expanding. This expansion stretches all light waves. The farther a galaxy is, the more its light has been stretched. Therefore, this Lyman-break at 912 Ångströms shifts to progressively longer, redder wavelengths with increasing distance. In a galaxy at a redshift of z equals 3, it shifts to 3,650 Ångströms. At z equals 7, it reaches about 7,300 Ångströms. and at z equals 14, like Jade's GSZ140, it is found in the near-infrared at almost 14,000 Ångströms. For the hypothetical galaxies at z equals 20 and z equals 30, the heroes of our story, this break would shift to about 19,000 and 28,000 Ångströms. The result is always the same, a sharp transition in the spectrum, a cliff that tells us this is where the great void begins. This method had been confirmed thousands of times and was an undeniable standard. But this method had a known failure mode. It had been documented in the scientific literature for at least a decade. Because the Lyman-break was not the only sharp transition that could appear in the colors of a faint infrared source. Much closer, for completely independent physical reasons, there was another type of object that created a break that looked almost identical in almost the same wavelength range. And these objects were the ultra-cool brown dwarfs in our own galactic backyard. A brown dwarf is a small, cold object whose mass and temperature are between that of a planet and a star. The coldest known ones, the Y-class, have surface temperatures between 250 and 500 Kelvin. At these extremely low temperatures, the atmosphere of a brown dwarf is not composed of individual atoms, but of numerous molecules. Methane, water vapor, ammonia, carbon dioxide, all of these are abundant. And each of these molecules has characteristic absorption bands at specific infrared wavelengths. It acts like a sponge that absorbs only certain colors of light. For example, methane has very strong absorption bands around 3.3 microns, and water at 1.4, 1.9, and 2.7 microns. The combined effect of all these molecular absorptions shapes the brown dwarf spectrum into a very characteristic form, with areas of relatively high emission separated by deep absorption troughs. For a Y-class brown dwarf with a temperature of 300 to 400 Kelvin, a special feature crucial for our story emerges in the spectrum. Water and methane absorption dramatically suppresses the brown dwarf's brightness in the near-infrared, but the same brown dwarf emits much more brightly at around 4 to 5 microns, in a region where there are fewer absorption bands. The result is a spectrum that rises sharply between the suppressed shorter wavelengths and the emission-rich long wavelengths. And this rise, this cliff, looks almost identical to the Lyman-break of a high redshift galaxy to the standard tools astronomers use to identify galaxy candidates. It's in the same wavelength range. It has the same general shape. In low-resolution photometry that measures brightness in only a few broad filters, the two are essentially indistinguishable. The universe, through two completely different physical processes, atomic absorption in the intergalactic medium and molecular absorption in a cold stellar atmosphere, had produced the same signature. This was the technical reason why the team waited for a year. They needed a test to distinguish between these two different scenarios, a test based not on color, but on motion. To perform this test, the team planned to use two of JWST's powerful instruments. The first was spectroscopy with NIRCam. The second was a second imaging epoch with NIRCam, a full year apart. Spectroscopy is like passing an object's light through a prism and splitting it into a rainbow. This shows us not just the brightness in a few filters, but the light intensity over a continuous range of wavelengths. On the night of March 27th, 2025, they observed both objects with NIRCam's prism mode. Prism mode is a low-resolution configuration, but it captures the entire wavelength range from about 0.6 microns to 5.3 microns in a single exposure. This was the perfect tool to see the overall spectral shape, the position of a break, and the broad absorption bands that distinguish different astrophysical objects. Within a few weeks, the data arrived, and the results made the story even more complicated. The signal was clear, the shape of both spectra was visible, but when they tried to fit a model to this shape, they found that both interpretations were consistent with the data. The brown dwarf models provided a statistically slightly better fit. The chi-squared values were a bit lower, but the galaxy models could not be definitively ruled out. The spectroscopy had shifted the team's suspicions towards the brown dwarf interpretation, but it had not provided conclusive proof. There was still a possibility. Everything was still possible. So, everything depended on that second test, that final proof, the proper motion test. Because What would ultimately distinguish these two possibilities was not the color of their light, but whether their position in space changed over time. To perform this test, they had to look at the same spot again for a full year. But during this 1-year wait, the world of science did not stand still. And other developments occurred that would affect the fate of these two red dots, especially as the mystery of the Capitaro ghost case deepened, providing a perfect case study for understanding the uncertainty the bullet cluster team was facing. Capitaro's mystery revolved around 3 main theories, and each one was absolutely incredible in its own right. The first, still the simplest and most impressive, was that Capitaro was indeed a galaxy at z=32. Proponents of this theory argued that although the photometric fit was extreme, it was not impossible, and the lensing effect of a nearby foreground galaxy could explain the unexpected brightness. This meant accepting that the first stars of the universe formed much, much more efficiently than expected. But the second, and increasingly strong, theory was that Capitaro was a brown dwarf. A paper published in 2026 by the Gandalf team presented rigorous analyses using model sets like Sonora Bobcat and Atmo 2020. According to these models, Capitaro could be a Y-class brown dwarf with a surface temperature between 300 and 400 Kelvin. The distance of this object from Earth would have to be between 127 and 1,800 parsecs. The probability of finding such an object in the Sears field was low, but not zero, especially given that such contaminants were systematically appearing. This was also the biggest concern for the Bullet Cluster team for their own candidates. But for Capitaro, there was a third, much more exotic theory. Andrea Ferrara and his team, and another group led by Mon Hong Lee, suggested that Capitaro could be a pair instability supernova at about z=15. This is the final moment of a very massive, primordial star with about 140 to 260 solar masses. Unstable electron-positron pairs begin to form in the star's hot core. This leads to a loss of pressure and triggers the star's collapse into itself. The result is a massive thermonuclear explosion that tears the entire star apart, leaving no remnant behind. The light curve of this explosion, its change in brightness over time, shows a slow dimming over weeks or months. And if this event occurs at a high redshift like z=15, cosmological time dilation stretches this light curve to years and shifts the spectral peak to long wavelength filters, just as was observed. So Capitaro was suspended between these 3 incredible possibilities: a galaxy at the dawn of the universe, a cold star in our backyard, or the death scream of a primordial giant. And the only thing that would distinguish these 3 scenarios was, just as with the bullet cluster objects, a measurement of proper motion. For Capitaro, the upper limit derived from the existing imaging baseline was not sensitive enough to distinguish a distant brown dwarf from a stationary galaxy. A more precise measurement required new observations, planned for late 2026. The whole community was waiting, and the Bullet Cluster team was waiting too. The summer of 2025 passed. They watched as the JWST and Sears teams published more evidence of brown dwarfs. A case study published by Kevin Hainline's team was particularly important: JWST BD9. This was a Y-class brown dwarf at a distance of about 2 kiloparsecs, with a measured proper motion of 20 milliarcseconds per year. This paper proved 3 important things. First, that JWST could measure milliarcsecond level proper motion over a time baseline of a few years. Second, that the motions of nearby brown dwarfs were indeed detectable. And third, that the combination of spectroscopy and astrometry could definitively identify a contaminant. Autumn came. The Sears team published their final analysis papers on Capitaro. The photometric fit favored the brown dwarf over the galaxy and supernova, but the uncertainties were still large. Winter came. The Bullet Cluster team prepared their analysis pipelines for the second imaging epoch. They wrote their astrometric registration scripts. They calibrated the expected systematic errors. They modeled the precision they would achieve based on the brightness of the targets, the angular resolution of NIRCam, and the available reference stars in the field. They expected a measurement with a precision of about 3 to 10 milliarcseconds per year. If the objects were galaxies, the measurement would be 0. If they were nearby brown dwarfs, they would give a value between 10 and hundreds of milliarcseconds per year. There would be no uncertainty. The result would be definitive. And the date for this second imaging epoch approached. All this technical preparation, all these theoretical discussions, all these parallel discoveries focused on a single moment. What would the telescope see when it looked at the same spot again, 1 year later? But what was truly exciting was not just the technical preparation, but the moment of truth itself that would rewrite the entire story. And then, the most incredible thing happened. The wait was over. January 21st, exactly 1 year and 1 day after the first observation. The NIRCam observations of the second epoch took place. The orientation was the same, the filters were the same, the integration times were adjusted. The data reached Earth within a few days. The analysis pipeline ran, the astrometric registration was completed, and the proper motion measurement was made. Now comes the moment for which everything was done, the moment of truth. Imagine that moment. A small office at a university, a late afternoon in the middle of winter. The processed images from the second epoch are on a screen window right next to the images from the first epoch a year ago. A team member for maybe a PhD student, maybe a postdoctoral researcher, opens the files in the same coordinate system and aligns them to the reference stars. The two faint red dots in the field. Those two dots that caused a year of careful, painstaking waiting. They are visible in both images, and it doesn't take a complex analysis to see the answer. A simple visual inspection is enough. This was the moment everything changed. The team member moves the cursor from the position of bullet BD1 in the first image to the position of bullet BD1 in the second image. It couldn't be, but it was. The cursor moved. A small but distinct amount. This was a movement that could never, ever be seen with the naked eye. This was a movement that required the angular resolution of the world's most powerful infrared telescope. But it was there. This dot had shifted a full 49 milliarcseconds across the sky in 12 months. That number alone was an earthquake. 49 milliarcseconds. This was a movement that a galaxy at the edge of the universe could never make in a year. Its proper motion should be effectively zero, but this was not zero. This was the definitive end of the greatest discovery in history, and at the same time, the beginning of a completely different, stranger discovery. The cursor moved to bullet BD2. It had moved to 24 milliarcseconds. Less, but still absolutely, undeniably different from zero. Both movements were in roughly the same direction. The angular distance between the two objects had hardly changed. The two faint red dots in the bullet cluster field were moving together. They were not at the edge of the universe. They had been in the Milky Way all along. All this time, they were slowly drifting across the sky at lateral speeds of about 116 kilometers per second, and these speeds were perfectly consistent with the kinematics of the Milky Way's thick disk. They had been here all along, hiding in plain sight in one of the most carefully studied regions of the sky. And now, there was no doubt left. With this result, the team went back to the NIRCam spectra they had been holding for 10 months. Previously, they had seen that the brown dwarf interpretation was statistically slightly better, but not definitive. Now, with the irrefutable evidence of proper motion, this data took on a whole new meaning. The brown dwarf interpretation was now the only valid interpretation. There was no more competition. They analyzed the spectra with a software called UCD-MCMC, applied to the Sonora Bobcat model set by Adam Burgasser and others. The results were clear. For bullet BD1, the best-fitting model gave a surface temperature of 350 Kelvin, with an uncertainty of plus or minus about 100 Kelvin. 350 Kelvin, that's about 77 degrees Celsius. The temperature of a cup of tea that has been sitting on the counter for a few minutes. Slightly cool to the touch, but still warm. For bullet BD2, the best-fitting model gave 410 Kelvin. That's about 137 degrees Celsius. Closer to the temperature of a slow oven, well above the boiling point of water. These were the surface temperatures of the objects that the world's most powerful infrared telescope was trying to interpret as galaxies at the dawn of cosmic time. The most distant thing in the picture was the temperature of a cup of tea. That fact alone summed up the entire incredible story. In two completely independent places in the universe, with two completely independent physical processes, they left the same fingerprint in our best data. On the one hand, the starlight of a galaxy from 100 million years after the Big Bang, filtered by the intergalactic hydrogen fog. On the other, the methane and water absorption in the atmosphere of a failed star 1,600 light-years away in our own galactic backyard. These two processes had absolutely nothing in common, but the result was the same. And this result was not just a coincidence. It revealed a deep truth about the method itself. The dropout method was not flawed. It worked exactly as it was designed to. The problem was that two completely different types of objects left indistinguishable signatures in the data on which the method was based. The problem was not the technique, it was in the physics itself. This coincidence was in nature itself, and this meant that some of the most extreme high redshift galaxy candidates catalogued so far might not be galaxies at all. They could be cold, local brown dwarfs wearing a spectral mask. The discovery by Bradach's team was not a one-off. It was a special example of a more general feature of the universe and the limits of the measurements we can make. The clean separation between the distant past and the local present turned out to be a bit blurry, and this blurriness was made of failed stars. With these thoughts, the team wrote the paper. They published it as a preprint on April 26, 2026. Their title was very clear: Two exciting high redshift galaxy candidates revealed as two exciting, ultra-cool brown dwarfs. And this paper questioned not only their own results, but also Capitoro, and thus a part of the High Z literature. The community largely accepted this result. It was the beginning of a cleanup operation. High Z catalogues were scanned. Proper motion follow-up observations for the most extreme candidates were accelerated. And this cleanup continues to this day. So, what does this tell us? It doesn't mean that the universe can't communicate with us. On the contrary, it says that it does communicate with us, but its language sometimes uses the same word for two completely different things. And our job as listeners is to learn the difference. The proper motion test is one way we learnt it. High-resolution spectroscopy that will be available in the future will be another. But, most importantly, this event taught us something. The nearest and the farthest in the picture can look the same because of a quirk of fundamental physics. And until we do the slow, patient work required to tell them apart, we should never assume we know what is what. This was not just the story of a galaxy hunt. It was the discovery of an unexpected homonym in the language of the universe. And this discovery helped us understand how we look at the universe, how crowded and mysterious our own galaxy is, and that some of the biggest secrets are sometimes hidden not in the most distant places, but right under our noses. But what exactly are these failed stars, these brown dwarfs? What makes them such good imposters? And how many more of them are there in the Milky Way? Because if the climax of this story is the revelation of the identity of these two dots, the heart of the story lies in understanding just how strange and unexpected that identity really is. To grasp the true meaning of this story, we need to understand what a Y-class brown dwarf actually is. Because the answer is one of the strangest and most fascinating categories of objects in all of modern astronomy, and it is the key to understanding just how crowded our own galaxy really is. A brown dwarf is, in its simplest sense, a failed star. Stars form from the gravitational collapse of cold interstellar gas clouds. As the cloud collapses, the temperature and pressure at the center increase, and at a critical mass, about 75 to 80 times the mass of Jupiter, the core becomes hot and dense enough to initiate sustained hydrogen fusion. A new star is born. But a brown dwarf is what happens when it falls just short of this threshold. The gas cloud is too small. The temperature at the center never reaches that critical value. Therefore, the resulting object has no nuclear engine to replace the heat it radiates into space. And so the brown dwarf cools relentlessly over billions of years. It slowly radiates the residual heat from its formation into space, becoming progressively fainter and colder as it ages. These failed stars are divided into different classes according to their temperature: M, L, T, and Y. M dwarfs are the hottest. L and T dwarfs are cooler. But the Y class is the coldest known category. Their temperatures are below 500 Kelvin. This class was only defined in 2011, based on cold objects discovered by NASA's WISE telescope, and the coldest members of this class are literally freezing. The coldest known brown dwarf, WISE J0855-0714, has a temperature of only about 250 Kelvin, that is minus 23 degrees Celsius, below the freezing point of water, and this object is only 7 light-years away from Earth. These objects are the true fossils of the universe. Because, for a brown dwarf to cool to 350 Kelvin, as in bullet BD1, an estimated 10 billion years must pass. The universe itself is only 13.8 billion years old. SO, bullet BD1 is an object that began to cool billions of years before the Sun formed, before the Earth formed. It is a small, faint, ancient record of our galaxy's youth. And now comes the truly shocking fact. These objects are not rare. Not at all. On the contrary, thanks to Webb's ability to look into the deepest and faintest regions of the infrared, we now understand that the Milky Way may be literally filled with these failed stars. The discovery by Bradach's team was just the tip of a massive, hidden iceberg, because, in parallel with their result, another research program conducted as part of the JADE survey began to reveal just how large this hidden population really is. Kevin Hainline and his team reported that they had identified 41 brown dwarf candidates in just the 2 Goods fields studied by JADES. Of these, 31 were T-dwarfs and 10 were Y-dwarfs. T-dwarfs were found up to a distance of 6 kiloparsecs, while the fainter Y-dwarfs were detected up to a distance of 2 kiloparsecs. When these numbers are extrapolated to the entire sky, the result is mind-boggling. It is estimated that there could be about 3,000 Y-dwarfs and 15,000 T-dwarfs in the sky detectable just to the depth of JADES. And these are only the ones we can see. The total population of Y-dwarfs in the Milky Way is in the tens of millions, if not hundreds of millions. The total population of all brown dwarfs may be comparable to, or even greater than, the number of normal stars in our galaxy. This completely changes our textbook picture of the Milky Way. Our galaxy is not just a place of hundreds of billions of bright stars, it is also a galaxy of invisible failed stars, whose number rivals that of the stars, quietly cooling for billions of years. They may be the most common type of star mass object in the entire universe. Bullet BD1 and Bullet BD2 were just 2 members of this massive hidden population. They were not the exception, they were the rule. Paper proved 3 important things. First, that JWST could measure milli-arcsecond level proper motion over a time baseline of a few years. Second, that the motions of nearby brown dwarfs were indeed detectable. And third, that the combination of spectroscopy and astrometry could definitively identify a contaminant. Autumn came. The Sears team published their final analysis papers on Capitoro. The photometric fit favored the brown dwarf over the galaxy and supernova, but the uncertainties were still large. Winter came. The Bullet Cluster team prepared their analysis pipelines for the second imaging epoch. They wrote their astrometric registration scripts. They calibrated the expected systematic errors. They modeled the precision they would achieve based on the brightness of the targets, the angular resolution of NIRCam, and the available reference stars in the field. They expected a measurement with a precision of about 3 to 10 milliarcseconds per year. If the objects were galaxies, the measurement would be 0. If they were nearby brown dwarfs, they would give a value between 10 and hundreds of milliarcseconds per year. There would be no uncertainty. The result would be definitive. And the date for this second imaging epoch approached. All this technical preparation, all these theoretical discussions, all these parallel discoveries focused on a single moment. What would the telescope see when it looked at the same spot again, 1 year later? But what was truly exciting was not just the technical preparation, but the moment of truth itself that would rewrite the entire story. And then, the most incredible thing happened. The wait was over. January 21st, exactly 1 year and 1 day after the first observation. The NIRCam observations of the second epoch took place. The orientation was the same, the filters were the same, the integration times were adjusted. The data reached Earth within a few days. The analysis pipeline ran, the astrometric registration was completed, and the proper motion measurement was made. Now comes the moment for which everything was done, the moment of truth. Imagine that moment. A small office at a university, a late afternoon in the middle of winter. The processed images from the second epoch are on a screen window right next to the images from the first epoch a year ago. A team member, for maybe a PhD student, maybe a postdoctoral researcher, opens the files in the same coordinate system and aligns them to the reference stars. The two faint red dots in the field. Those two dots that caused a year of careful, painstaking waiting. They are visible in both images, and it doesn't take a complex analysis to see the answer. A simple visual inspection is enough. This was the moment everything changed. The team member moves the cursor from the position of bullet BD1 in the first image to the position of bullet BD1 in the second image. It couldn't be, but it was. The cursor moved. A small but distinct amount. This was a movement that could never, ever be seen with the naked eye. This was a movement that required the angular resolution of the world's most powerful infrared telescope. But it was there. This dot had shifted a full 49 milliarcseconds across the sky in 12 months. That number alone was an earthquake. 49 milliarcseconds. This was a movement that a galaxy at the edge of the universe could never make in a year. Its proper motion should be effectively zero, but this was not zero. This was the definitive end of the greatest discovery in history, and at the same time, the beginning of a completely different, stranger discovery. The cursor moved to bullet BD2. It had moved to 24 milliarcseconds. Less, but still absolutely, undeniably different from zero. Both movements were in roughly the same direction. The angular distance between the two objects had hardly changed. The two faint red dots in the bullet cluster field were moving together. They were not at the edge of the universe. They had been in the Milky Way all along. All this time, they were slowly drifting across the sky at lateral speeds of about 116 kilometers per second, and these speeds were perfectly consistent with the kinematics of the Milky Way's thick disk. They had been here all along, hiding in plain sight in one of the most carefully studied regions of the sky. And now, there was no doubt left. With this result, the team went back to the NIRCam spectra they had been holding for 10 months. Previously, they had seen that the brown dwarf interpretation was statistically slightly better, but not definitive. Now, with the irrefutable evidence of proper motion, this data took on a whole new meaning. The brown dwarf interpretation was now the only valid interpretation. There was no more competition. They analyzed the spectra with a software called UCD-MCMC, applied to the Sonora Bobcat model set by Adam Burgasser and others. The results were clear. For bullet BD1, the best-fitting model gave a surface temperature of 350 Kelvin, with an uncertainty of plus or minus about 100 Kelvin. 350 Kelvin, that's about 77 degrees Celsius. The temperature of a cup of tea that has been sitting on the counter for a few minutes. Slightly cool to the touch, but still warm. For bullet BD2, the best-fitting model gave 410 Kelvin. That's about 137 degrees Celsius. Closer to the temperature of a slow oven, well above the boiling point of water. These were the surface temperatures of the objects that the world's most powerful infrared telescope was trying to interpret as galaxies at the dawn of cosmic time. The most distant thing in the picture was the temperature of a cup of tea. That fact alone summed up the entire incredible story. In two completely independent places in the universe, with two completely independent physical processes, they left the same fingerprint in our best data. On the one hand, the starlight of a galaxy from 100 million years after the Big Bang, filtered by the intergalactic hydrogen fog. On the other, the methane and water absorption in the atmosphere of a failed star 1,600 light-years away in our own galactic backyard. These two processes had absolutely nothing in common, but the result was the same. And this result was not just a coincidence. It revealed a deep truth about the method itself. The dropout method was not flawed. It worked exactly as it was designed to. The problem was that two completely different types of objects left indistinguishable signatures in the data on which the method was based. The problem was not the technique, it was in the physics itself. This coincidence was in nature itself, and this meant that some of the most extreme high redshift galaxy candidates catalogued so far might not be galaxies at all. They could be cold, local brown dwarfs wearing a spectral mask. The discovery by Bradach's team was not a one-off. It was a special example of a more general feature of the universe and the limits of the measurements we can make. The clean separation between the distant past and the local present turned out to be a bit blurry, and this blurriness was made of failed stars. With these thoughts, the team wrote the paper. They published it as a preprint on April 26, 2026. Their title was very clear: 2 exciting high redshift galaxy candidates revealed as 2 exciting, ultra-cool brown dwarfs. And this paper questioned not only their own results, but also Capitoro, and thus a part of the High Z literature. The community largely accepted this result. It was the beginning of a cleanup operation. High Z catalogues were scanned. Proper motion follow-up observations for the most extreme candidates were accelerated. And this cleanup continues to this day. So, what does this tell us? It doesn't mean that the universe can't communicate with us. On the contrary, it says that it does communicate with us, but its language sometimes uses the same word for 2 completely different things. And our job as listeners is to learn the difference. The proper motion test is one way we learnt it. High-resolution spectroscopy that will be available in the future will be another. But, most importantly, this event taught us something. The nearest and the farthest in the picture can look the same because of a quirk of fundamental physics. And until we do the slow, patient work required to tell them apart, we should never assume we know what is what. This was not just the story of a galaxy hunt. It was the discovery of an unexpected homonym in the language of the universe. And this discovery helped us understand how we look at the universe, how crowded and mysterious our own galaxy is, and that some of the biggest secrets are sometimes hidden not in the most distant places, but right under our noses. But what exactly are these failed stars, these brown dwarfs? What makes them such good imposters? And how many more of them are there in the Milky Way? Because if the climax of this story is the revelation of the identity of these 2 dots, the heart of the story lies in understanding just how strange and unexpected that identity really is. So, to grasp the true meaning of this story, we need to understand what a Y-class brown dwarf actually is. Because the answer is one of the strangest and most fascinating categories of objects in all of modern astronomy, and it is the key to understanding just how crowded our own galaxy really is. A brown dwarf is, in its simplest sense, a failed star. Stars form from the gravitational collapse of cold interstellar gas clouds. As the cloud collapses, the temperature and pressure at the center increase, and at a critical mass, about 75 to 80 times the mass of Jupiter, the core becomes hot and dense enough to initiate sustained hydrogen fusion. A new star is born. But a brown dwarf is what happens when it falls just short of this threshold. The gas cloud is too small. The temperature at the center never reaches that critical value. Therefore, the resulting object has no nuclear engine to replace the heat it radiates into space. And so the brown dwarf cools relentlessly over billions of years. It slowly radiates the residual heat from its formation into space, becoming progressively fainter and colder as it ages. These failed stars are divided into different classes according to their temperature: M, L, T, and Y. M dwarfs are the hottest. L and T dwarfs are cooler. But the Y class is the coldest known category. Their temperatures are below 500 Kelvin. This class was only defined in 2011, based on cold objects discovered by NASA's WISE telescope, and the coldest members of this class are literally freezing. The coldest known brown dwarf, WISE J0855-0714, has a temperature of only about 250 Kelvin, that is minus 23 degrees Celsius, below the freezing point of water, and this object is only 7 light-years away from Earth. These objects are the true fossils of the universe. Because, for a brown dwarf to cool to 350 Kelvin, as in bullet BD1, an estimated 10 billion years must pass. The universe itself is only 13.8 billion years old. So, bullet BD1 is an object that began to cool billions of years before the Sun formed, before the Earth formed. It is a small, faint, ancient record of our galaxy's youth. And now comes the truly shocking fact. These objects are not rare. Not at all. On the contrary, thanks to Webb's ability to look into the deepest and faintest regions of the infrared, we now understand that the Milky Way may be literally filled with these failed stars. The discovery by Bradach's team was just the tip of a massive, hidden iceberg, because, in parallel with their result, another research program conducted as part of the JADE survey began to reveal just how large this hidden population really is. Kevin Heinlein and his team reported that they had identified 41 brown dwarf candidates in just the 2 Goods fields studied by JADES. Of these, 31 were T-dwarfs and 10 were Y-dwarfs. T-dwarfs were found up to a distance of 6 kiloparsecs, while the fainter Y-dwarfs were detected up to a distance of 2 kiloparsecs. When these numbers are extrapolated to the entire sky, the result is mind-boggling. It is estimated that there could be about 3,000 Y-dwarfs and 15,000 T-dwarfs in the sky detectable just to the depth of JADES. And these are only the ones we can see. The total population of Y-dwarfs in the Milky Way is in the tens of millions, if not hundreds of millions. The total population of all brown dwarfs may be comparable to, or even greater than, the number of normal stars in our galaxy. This completely changes our textbook picture of the Milky Way. Our galaxy is not just a place of hundreds of billions of bright stars, it is also a galaxy of invisible failed stars, whose number rivals that of the stars, quietly cooling for billions of years. They may be the most common type of star mass object in the entire universe. Bullet BD1 and Bullet BD2 were just 2 members of this massive hidden population. They were not the exception, they were the rule. Therefore, a revision of the dropout method was inevitable. The method was not flawed, but it turned out to have a massive blind spot. Charles Steidel's original 1996 paper could not have predicted this failure mode, because, at that time, neither the existence of such cold brown dwarfs was known, nor could our telescopes look at such high redshifts. The galaxies Steidel was looking for were around Z=3, and the Lyman-break in this region did not overlap with the spectral signature of a brown dwarf. But, when we looked at Z=20 and Z=30 with JWST, these 2 completely different physical processes perfectly aligned to leave the same signature at the same wavelength. The collision was inevitable, and the consequences of this collision began to shake the high-Z catalogues. The systematic work of Heinlein and his team estimated that about 0.1% of the high-Z galaxy candidates in JADES and SEERS could actually be brown dwarfs. This rate may seem small, but when a survey like JADES reveals tens of thousands of candidates, this means dozens of misidentifications. And for the most extreme, highest Z-value candidates, this contamination rate increased significantly. The case of JADES GS-BD9 proved this. This object was initially catalogued as a galaxy candidate at Z=12, but follow-up observations showed that it was actually a brown dwarf moving at a speed of 214 kilometers per second. This was irrefutable proof of how necessary the cleanup operation was. The most exciting candidates were the most suspicious ones, and this whole story brings us back to Capitoro, to that great mystery still unsolved. The fate of Bullet BD1 and BD2 was sealed by the proper motion test. But Capitoro's fate was still awaiting those second epoch observations at the end of 2026. That single picture would show which of the 3 incredible scenarios was true. But we know now that our understanding of the boundaries of the universe and our own galaxy has changed forever. All these epic moments, these record-breaking numbers, these shattered theories have brought us to a point where we must stop and think. All these discoveries have fundamentally changed our understanding of the universe. But now we must ask a deeper, more fundamental question. What does all this mean for us who are trying to understand our own place in this immeasurable cosmos? Now is the time to move away from the data, to take our eyes off the telescopes and look inside, at the philosophical contradictions this story awakens within us. Let's start with the most fundamental contradiction, the surprising similarity of the most distant to the nearest. On one hand, we are looking for objects at the farthest corners of the universe, at the beginning of time. Galaxies formed just a few 100 million years after the Big Bang. Their light has been reaching us for more than 13 billion years. They represent the largest scales of the universe, the most ancient times, the most fundamental structures. To look at them is to look back in time, to look at our own origins. This is one of humanity's deepest, most philosophical quests. On the other hand, right in the middle of this quest, in the same pictures, are objects standing right under our noses. In our own galaxy, a brown dwarf 1,600 light-years away is our direct neighbor cosmologically. Its light reaches us in only 1,600 years, a period almost 10 million times shorter than the travel time of light from a galaxy at z=14. These proportions are absolutely brutal. This is the tragic truth of this contradiction. There are homonyms in the language of the universe that can deceive us. While trying to achieve our greatest, noblest goals, trying to understand the origin of everything, we can encounter unexpected, hidden obstacles that can lead us astray. This reminds us how fragile our certainty is, that even our most robust methods that have worked for 30 years can have blind spots. But there is also a wonderful side to this situation, because it shows how creative and full of unexpected connections the universe is. The chemistry in the atmosphere of a failed star, the temperature of a cup of tea, and the atomic physics that filters the light of a galaxy at the dawn of the universe can pretend to tell us the same story. This shows that the music of the universe sometimes meets at the same notes on completely different scales, and you, the one listening to this story, are standing right in the middle of this contradiction. You too live in your own small local world, and at the same time, you can travel to the farthest corners of the universe in your mind. You too must be wary of illusions that can lead you astray, and at the same time, you must appreciate the beauty of these strange, poetic connections of the universe. To realize that while looking at the farthest, we are actually discovering the nearest. The hidden population of our own galaxy is one of the deepest lessons of this journey. This brings us to a second, equally profound contradiction: the paradox of crowded loneliness. On one hand, there is the truth that JWST has shown us. The Milky Way is much, much more crowded than we thought. It is not just a place of hundreds of billions of bright stars. It is also a galaxy of perhaps as many invisible, failed stars, quietly cooling for billions of years, whose number rivals that of the stars. Our galaxy is full of quiet, cool things we cannot see, and these quiet things have been here much longer than the shining ones. This is an incredibly comforting thought on one hand. We are not alone in the universe. Our own galaxy is full of billions of neighbors we knew nothing about, we didn't notice. They, just like us, are part of the fabric of the galaxy. This shows that the galaxy is not just made of bright islands floating in empty space, but also has an invisible but existing population that connects these islands. On the other hand, there is a tragic side to this crowd. We will never be able to communicate with these billions of neighbors. They drift unknowingly on their own paths in the galaxy. So do we. They are unconscious, lifeless objects that have been cooling for 10 billion years. Knowing of their existence can make our cosmic loneliness even sharper. We have billions of neighbors, but they are all mute, like the feeling of being alone in a crowded room. But this contradiction also has a beautiful but. Yes, we cannot talk to them, but we can read their story. Each brown dwarf is a window into our galaxy's past. Their temperature tells us their age, their chemical composition tells us the properties of the gas cloud from which they were born. They are the silent witnesses who wrote the history of the Milky Way. By studying them, we can understand what the galaxy looked like before the sun was born. This is a kind of time travel, and you are also a part of this crowded loneliness. You too can feel alone in your own life, even when surrounded by people. But at the same time, you know that every person around you, just like these brown dwarfs, is the carrier of a unique story, of a billion-year evolutionary history. And even though we can't always talk to all of them, we can learn something from their existence, from their stories. Therefore, the discovery of this hidden population of our galaxy is not just an astronomical curiosity, but also an effort to understand our own place, our own connections. But there is another point we need to go deeper into on this philosophical journey: the nature of knowledge and the limits of our ability to understand. And so now we face one of the most fundamental contradictions of the nature of knowledge: that thin, blurry line between what we know and what we may never know. On one hand, there is the incredible, almost godlike power of the human mind and the science it has created. With a telescope floating 1.5 million kilometers from Earth, we can capture the light of a 13.5 billion-year-old galaxy. We can split this light into its spectrum and understand its chemical elements, its temperature, and its mass. By measuring a shift thinner than a human hair in two images taken a year apart, we can calculate the speed of an object 1,600 light-years away as 116 kilometers per second. This is the absolute triumph of reason. It is the result of hundreds of years of accumulation, patience, and unrestrained curiosity. It is the most solid proof of our ability to decipher the language of the universe. On the other hand, there is the tragic, humbling truth that this very story shows us. Even our best tools, our most sophisticated methods can be wrong. The universe can set traps for us. It can cleverly deceive us. A method that worked flawlessly for 30 years can suddenly deceive us on one of our biggest and most important goals. This shows how temporary and fragile knowledge is. Something we accept as an absolute truth today can be shaken tomorrow by a new observation, new data. This is a humbling, almost sad truth. We can never be completely sure. We must always leave a door open for a little doubt, for the unexpected. But there is an infinite beauty in this very situation, because this is precisely why the progress of science is possible. Science is not a collection of dogmas that claims to have reached absolute truths. It is a process that constantly questions itself, finds its own mistakes, and corrects them. This is exactly what Bradach's team did. They followed their doubts, perhaps at the cost of missing out on the greatest discovery in history, and in the process, they discovered something much more important: the truth. This self-correcting mechanism of science is its greatest strength, and you live this contradiction every day in your own life. You learn things, you become sure of things, but you also know how open you are to mistakes. And your greatest moments of learning are often the moments you realize your biggest mistakes. Therefore, the universe deceiving us is not a failure, it is an opportunity to look deeper, to ask more questions, and ultimately, to reach a more accurate, more honest understanding. This brings us to another, perhaps the most personal, contradiction. The contradiction between meaning and meaninglessness. On one hand, there is the absolute indisputable meaninglessness of a Y-class brown dwarf. It is a cold ball of gas, a little bigger than Jupiter, that has existed for 10 billion years and emits almost no light. There is no life on it, no consciousness, no purpose. It just exists. And it will continue to exist for billions more years, doing nothing, affecting nothing. In the grand scheme of the universe, it is just a statistic, just one of hundreds of billions of similar objects. This is the purest form of how indifferent and purposeless the universe can be. This is a tragic truth that reminds us how small and perhaps futile the human search for meaning is in the face of this vast, cold, and indifferent cosmos. But, on the other hand, there is the incredible meaning we attribute to this meaningless object. For us, Bullet BD1 is not just a ball of gas. It is a key to understanding the secret history of our own galaxy. A touchstone that tests the limits of our best telescopes, a symbol of how the universe can speak to us in unexpected ways. We looked at this cold, unconscious object and saw a story in it. We learned a lesson, we created meaning, and this is the most fundamental characteristic of being human. The universe itself may be meaningless, but our effort to understand it is not meaningless. On the contrary, it is perhaps the only truly meaningful thing in this universe. This is a wonderful, almost consoling ray of hope, shining in the midst of a sad, cold loneliness. And you are at the center of this process. Your own life may be just a temporary flicker on the grand scale of the universe, but in this brief moment, you have the ability to give meaning to the world around you, to other people, even to a cold ball of gas. 1,600 light-years away, your curiosity, your questions, your effort to understand is what gives meaning to this indifferent universe. That's why the story of a brown dwarf is actually our story of creating meaning in the midst of meaninglessness. All these philosophical thoughts, these great contradictions, show how complex and multi-layered the universe and our place in it are. On one hand, the unimaginable size of the universe and our smallness. On the other, the surprising similarity of the most distant to the nearest. On one hand, the crowded loneliness of our own galaxy, and on the other, our ability to create meaning despite the fragility of knowledge. We now know that the boundary between our own galaxy and the rest of the universe is not a sharp, clear wall as we thought, but a curtain of fog made of failed stars. We now know that the greatest discoveries are sometimes made when we realize our biggest mistakes. But after all we have learnt, one more question remains in our minds, perhaps the most important one. Are these objects, these failed stars, just contaminants, just obstacles on our way to searching for distant galaxies, or do they have a deeper, more personal story to tell us? Because to call an object a failed star is to stick a label on it based on our own expectations. But what if for the universe itself, there is no concept of success or failure? What if everything is just as it should be? This thought takes us to another, even deeper place. A place that deals not only with our place in the universe, but with the meaning of knowledge itself and what we do with that knowledge. First, let's consider the contradiction between the power that knowledge gives us and the deep helplessness it creates at the same time. On one hand, we now know. We know that the Milky Way is filled with brown dwarfs, whose numbers may rival those of the stars, secretly cooling for billions of years. This is an incredible power, because this knowledge allows us to redraw the map of our galaxy. It can affect our star formation models, our galactic evolution theories, and even our understanding of dark matter by providing a possible source for mass. This knowledge gives us a sense of control over the workings of the universe that we never had before. We can now search for these objects in a targeted way, classify them, and solve their secrets. This is the path from the darkness of ignorance to the light of understanding. On the other hand, there is a tragic, almost paralyzing helplessness that comes with this knowledge. We know of the existence of these billions of objects, but we can change absolutely nothing about them. They have been drifting in their own predetermined orbits for 10 billion years, and they will continue to drift for billions more years after our discovery. Their fate is completely independent of our knowledge. This reminds us how immeasurably large the universe is, and how infinitely limited our actions are. Knowledge does not always mean control. Sometimes, knowledge simply means becoming aware of one's own helplessness. But, even in this helplessness, a wonderful, almost stoic truth is hidden. Yes, we cannot change their fate, but we can change our own. This knowledge inspires us. It gives us a reason to ask more questions, to build better telescopes, to look deeper. This knowledge makes us more curious, more knowledgeable, more conscious beings, and you live this contradiction in your own life. You know the big problems of the world, the injustices, the inevitable ends, and you can feel helpless in the face of it. But at the same time, this knowledge also gives you the power to act, to do things better, to make a difference in your own small world. Knowledge is both a burden and a gift, and we are beings trying to find a balance between the two. This brings us to a second deep contradiction, the two faces of time, the overwhelming weight of the past, and the liberating lightness of the future. On one hand, there is an incredible, almost unimaginable past that an object like Bullet BD1 carries, an age of about 10 billion years. This is a story almost as old as the universe itself. It was drifting in our galaxy even before the solar system formed. It was there when dinosaurs roamed the Earth. All of recorded human history is just a blink of an eye in its lifetime. This past has an overwhelming weight. This is a tragic truth that hits us in the face with how new and how temporary our own existence is. We are just the last second of a billion-year history that these ancient objects silently witnessed. This can make us feel insignificant, a fleeting moment in an eternal story. But time also has another, hopeful face. This brown dwarf will continue to exist for billions more years. It will slowly cool, darken, and eventually come into thermal equilibrium with the background temperature of the universe. Its future is largely predetermined, a monotonous, slow, silent death. But our future, your future, is uncertain. It is light. It is full of possibilities. Unlike this brown dwarf, we have the potential to shape our own future. We decide what we will do tomorrow, what we will learn, what we will create. This is an incredibly beautiful and hopeful freedom that stands against the massive weight of the past. And you live at the intersection of these two times. You carry the weight of your own past, your family, your culture, your experiences, but you also have the lightness of the infinite possibilities that each new day brings. You cannot change your past, but you can write your future. The story of a 10-billion-year-old brown dwarf reminds us of just that. No matter how deep and overwhelming the past is, the future is always a blank page waiting to be written. And finally, we must face perhaps the most unsettling contradiction. The contradiction between the silence of the universe and the sound we create. On one hand, there is the absolute deafening silence of a large part of the universe. These brown dwarfs have been silent for 10 billion years. They say nothing, they send no messages. Their existence is revealed only by the faint photons captured by our telescopes that we accidentally pointed at them. This is a tragic truth that reminds us that the fundamental nature of the universe is silence. The universe makes no effort to talk to us, it just exists. And our effort to understand it is a one-sided step against this great cosmic silence. This is a deep, existential feeling of loneliness. We have billions of neighbors, but none of them answer us. On the other hand, there is the incredible sound we create in the midst of this silence. The sound of science, the sound of art, the sound of philosophy. The words we use to tell this story. The paper Bradach's team wrote about their findings. The lines of code that analyze this data. All of this is our effort to give meaning to this silent universe, to interpret it, to tell a story about it. We are the beings who turn the silence of the universe into sound. This is an incredibly powerful and beautiful role. We are a part of the universe through which the universe knows itself, thinks about itself. Our existence gives a consciousness, a voice, to this silent cosmos. And you are a part of this voice. Your thoughts, your questions, the echoes that form in your mind as you listen to this story are sounds against this great silence. You are not just a passive observer. You are an active participant in this universal dialogue, and every question you ask, every curiosity you feel, breaks this silence a little more. Therefore, instead of despairing in the face of the universe's silence, we should remember how valuable our own voice is. Because, if it weren't for us, there would be no one to tell the story of these brown dwarfs. They would have remained in silence forever. But after all this inner journey, as we approach the end of the story, one more question remains. With everything we have learned, with this new perspective, what should we see now when we look at the night sky? But these thoughts lead us to another, final place. With everything we have learned, with this new, more complex perspective, what should we see now when we look at the night sky? Because this story is not just the story of an astronomical discovery. It is also a journey that has changed our perspective forever, and at the end of this journey, the sky can no longer be the same. First, we must face the invisible reality behind the visible. On one hand, there is that magnificent, familiar sight you see when you look at the sky on a clear, dark evening, away from the city lights. Thousands of stars with the naked eye, the faint, milky band of the Milky Way, perhaps in the darkest skies, with the sharpest eyes, the faint smudges of distant galaxies. This is an impressive picture that has inspired humanity for thousands of years. This is the face the universe shows us. On the other hand, there is a tragic yet fascinating truth that this story has taught us. What we see is only a tiny, shining part of the whole picture. In this sky, for every bright star we can see, there are perhaps even more invisible, silent, cold objects. Billions, perhaps hundreds of billions of brown dwarfs, free-floating planets, cold gas clouds. They are there, but completely invisible to our eyes. This is sad on one hand, because it shows that a large part of the universe, perhaps the largest part, is hidden from us, that we can never fully grasp its true richness and complexity. But there is an incredibly beautiful side to this situation. It means that the universe always has new secrets to be discovered. No matter how much we learn, there is always more. The fuel for our curiosity will never run out. An instrument like the James Webb telescope has opened the curtain of this invisible universe just a tiny crack. And even what we have seen through this crack has changed our whole picture. SO, the next time you look at the night sky, you should no longer see just those bright dots. You should know that the darkness between those bright dots is not really empty. That darkness is filled with billion-year-old fossils, silent neighbours, countless stories waiting to be told. You are now looking with eyes that know the unseen also exists. And that is a much richer, much deeper look. This brings us to the second and final contradiction of this journey, the contradiction between the separateness of the parts and the wholeness of existence. On one hand, there is the analytical perspective that science has taught us, and that is absolutely necessary. We break the universe into parts: stars, galaxies, brown dwarfs, planets. We classify them. We stick labels on them according to their temperature, mass, distance. Bullet BD1 is a Y-class brown dwarf. JWST 14-0 is a galaxy at Z equals 14.32. This is a necessary method to understand the world, to break down immeasurable complexity into manageable, understandable parts. This is the basis of all knowledge. But there is also a tragic side to this analytical perspective. Sometimes, these classifications prevent us from seeing the deep, fundamental connection between objects, the wholeness. When we put everything in its own box, we can lose sight of the invisible threads between these boxes. We can start to see the universe not as a living, interconnected whole, but as a collection of objects. And one of the most beautiful lessons this story has taught us is precisely this wholeness. This story showed how unexpectedly and deeply interconnected the most distant galaxy and the nearest failed star can be. Although they are fundamentally different objects, they are subject to the same universal laws of physics. Their light travels in the same space-time and can pretend to speak the same language in our telescopes. This is a poetic, almost mystical reminder that everything in the universe, from the smallest to the largest, from the oldest to the newest, is somehow connected. We are just a part of this cosmic web, and you are also a part of this wholeness. You are not just a collection of labels, roles, and identities. You are the result of billions of years of cosmic evolution. The atoms in your body were forged in stars billions of years ago, and you, with your ability to understand this story, are an instrument through which the universe knows itself. So, when you look at the night sky, you should no longer see just separate isolated objects. You should see the parts of a great cosmic fabric, and you should feel that you too are a thread in this fabric. At the end of this long inner journey, we find ourselves with the answer to the simple question we asked at the beginning. What did the James Webb telescope find when it looked at the bullet cluster? The answer was much more complex and much more beautiful than expected. It didn't just find the potentially most distant galaxy candidates in the universe. It also found two of the oldest, coldest, and most hidden inhabitants of our own galaxy. It didn't just find data that challenged our cosmological models. It also found a mirror that made us question our view of the universe and our own place in it. We now know that the boundary between the most distant and the nearest is blurry. We now know that the Milky Way is full of silent, invisible neighbours, and we now know that even the universe's deceptions are a door to deeper truths. This journey was more about asking better, deeper questions than finding a definitive answer, and these questions led us to understand not only the universe, but ourselves better. We started with a simple rule that had been valid for 30 years, and we watched it get shattered by two tiny red dots. We discovered that the greatest cosmic deception took place not at the edge of time, but right under our noses. We now know that the boundary between the most distant and the nearest is blurred by a curtain of failed stars. We know that our own galaxy is filled with billions of silent, invisible neighbours carrying the ancient history of the cosmos. And we now know that even our greatest misconceptions are a door to deeper truths. At the end of this journey, we see that the most distant point in the picture is the temperature of a cup of tea, and this awareness alone has changed our perspective forever. And you are part of this new perspective. You are not just an observer. You are a being who can notice the complex and poetic connections of the universe. Your ability to doubt, to question, and finally to understand is the greatest power we have against the immense silence of the cosmos. If the journey of uncovering the universe's deceptions and reassessing our place within it has also affected you, share your thoughts in the comments and subscribe for new journeys to the limits of knowledge. Because On this journey, we looked at the first 100 million years of the universe, but I haven't told you the most important thing yet. On this journey, we looked at the first 100 million years of the universe, but I haven't told you the most important thing. The entire fate of the universe was written in the first 3 minutes. The building blocks of everything that exists today were forged in those first 180 seconds. On our next journey, we will go to those first moments. Are you ready to witness the beginning of time?